Okay, so far we've taken a look at velocity-dependent forces using analytic techniques. And I'd like to go take a look now into using computational techniques. And this will be useful because oftentimes most things we have to solve in physics are differential equations. And as you go on in your physics career, you will learn many ways of tackling things analytically. But, we've been at this game for a few hundred years, and we're kind of getting to the point where, for a lot of problems, if there was an analytic approach, probably someone would have found it by now, or at least a useful analytic approach. And so now we're having to rely more and more on numeric technique. So we'll start by just giving a very basic sketch of how this could work. And as always with anything like this, let's drop a rock. So literally we're just dropping a rock. We're going to do no air resistance for now. So we can go ahead and make down positive for my rock. Let's assume that we're dropping it at rest. And the initial time is 0, just to make the math a little easier. And we're only going to have one force, and that is gravity acting down on it. Okay. What we would like to find is y of t. Now, this is something that we know darn well how to solve. Then you can just integrate it twice. I want to just kind of visit this for the flavor of how you would do it analytically. So a bad approach, and I'm just going to warn you right now it's bad, but it's instructive, would be a forward Newton method. Now, Newton's method is not necessarily that bad. Just for this particular variant, the forward Newton, while intuitive, has problems. So what we can do is we can just kind of imagine making ourselves a little table. We can say, okay, at t equals 0, we have v equals 0. A is 9.8 meters per second squared, and y is 0. Okay, so now what we can imagine doing is using these values to get us the next values. So let's find the values, say at t equals 0.001 seconds. So increment by 1,000th of a second. All right, well, we can find v, that will be 0, what we had before, plus our acceleration, 9.8 meters per second squared, times the time elapsed, 1,000th of a second. And so we get that our new velocity at time 0.001 seconds is 0.0098 meters per second. And then to get our position, we would just do the same thing. We'd say that, well, the initial position was 0. We take the velocity from the previous time step, multiply that by the time elapsed, and we are still at 0. So you can already see this is a little hanky. How can we have a speed and yet we hadn't moved? And that's sort of the problem with this method. And we'll see where that takes us. All right, so we can then imagine going to 2,000ths of a second, and we play exactly the same game. So what's our new speed? Well, we take the old one, stick it in, 0.0098 meters per second, and then we take our acceleration, 9.8 meters per second squared, times the time difference, 0.001 seconds, and now we are at 0.0196 meters per second. And now for our position, we say that it's equal to 0, because that was the previous step, plus, well, finally we were moving at the last time step, 0.0098 meters per second times the time step of 0.001 seconds. And we get that our object is located now at 0.000098 meters. And you repeat this forever, or at least until you get what you need. So I think you can see, though, just from looking at the t equals 1,000th of a second, it makes no sense for it to be moving but to have not moved. And in fact, at every step, this error that we get of just using the old velocity as the current velocity continues to magnify. Now, there's at least two ways out of this. Otherwise, we wouldn't even be attempting numeric techniques, because if you try doing it this way, you'll find very quickly that your answers go to crap. One way is to realize that when you differentiate something, when you take the limit, you're approaching from both sides of the interval. So if we take that idea and just say, we're replacing our derivatives here with differences, there'd be a better approximation to say that that velocity that we calculated at t equals 1/1000th of a second here, that's it would actually have been better for us if we had calculated a velocity at 0.5 and then we used that velocity at 0.5 to feed into here to get a position at 1,000th. And then we can jump ahead and get the velocity at 1.5 and use that to get the position at 2,000ths and so forth. That's called a midpoint Newton method. And it turns out that for gravity, the errors associated with that actually all pretty much cancel themselves out. You're just left with intrinsic issues of the machine can only represent so many digits. Okay, so sometimes you get lucky like that, and that's why I mentioned the Newton method at all. However, for most problems, you're not going to have that clean of a cancellation happen. And so there's a class of techniques called Predictor-Corrector Methods, where what you would do is you would say, okay, let's go ahead and compute our velocity at time 1/1000th of a second, and then we'll go ahead and use that to go backward, and then that will give us an error in our position and velocity, which will allow us to come up with a better guess for what the values of v and y should be at this time. So it's called a predictor-corrector method. You step forward, and then you actually just use that data to step back. You see how much you missed your starting point by, and you keep tweaking it around until you jump back to where you started. There's a whole collection of these techniques. Probably the favorite technique is the class of methods called the Runge-Kutta Method, and for whatever reason it's kind of well known in the computational physics lore that the fourth order Runge-Kutta method is sort of the happiest. You don't really need to worry about that so much if you're using Mathematica, because Mathematica is pretty darn good about looking at the situation and guessing what technique would be best, although sometimes it can get itself into a little bit of trouble, and then you can give it a hint as to what technique would be best. But I mentioned this because at some point you may find yourself writing a big pile of C or Fortran, and you have to manage that yourself, and so you should be aware. Certainly, if you're looking for math courses to take, a course in numeric methods is very useful. Okay, just another little tidbit. I'm not quite sure where to throw in, but I think it's probably, this is a good place to do it as any, is scaling. Now this gets to how computers actually represent numbers. When you do floating point arithmetic, you're only allowed so many binary digits to represent your value. And so it does it in a binary version of scientific notation, where you have the mantissa, which is the number in front of the times, and then the exponent, which we would normally be doing as times 10 to the whatever. A computer does as times 2 to the whatever, but that doesn't matter really for us. And nowadays, the typical amount of memory that a computer will allocate to a floating point number will allow for a pretty big dynamic range of values. You might be able to go down to, say, like 10 to the negative 1,000 to 10 to the plus 1,000 or something like that. Where you can get yourself into a bit of trouble is if you're working with astronomical values. That's why they call them astronomical numbers. There you have such large numbers and such small numbers that you can start to get the problem that if you multiply two of them together, you divide two of them together. If you're not careful about the order you do them in, you can either get yourself an overflow or an underflow, and that's not good. And at the just before that kind of thing happens, you can get yourself into a case where you start losing precision, and that's not good either. So generally, it's a good idea to try to work with values around 1. Oops, sorry about that. Try that again. Work with values around 1. Okay. And so a lot of times you'll redefine variables to get closer to that sort of ideal. So, we could imagine, say, when we looked at our linear free fall with air resistance, we had gravity down minus air resistance equaled m dv dt. So we can rewrite this to get the v all by itself, mg over c1 minus v equals m over c1 dv dt. Now we remember from before that this much here was our v terminal, and that much there was our time constant. So we can rewrite that some more as v terminal minus v equals tau dv dt. So if I divide everything through by v terminal, this gives me a natural scale for the velocity. It's going to hang around, when it gets a terminal velocity, v will equal v terminal. So that's sort of a natural scale. So let's divide by it. So we get 1 minus v over v terminal equals tau over v terminal dv dt. Now, if we think about that just a little more, we can, going back to our definition of v terminal and tau, we can rewrite this or sorry, don't even have to go back to definition. We can just rewrite this cleverly as dv over v terminal and dt over tau. Okay, so that gives us a good clue as to what would be some natural values to use. So if we let u equal v over v terminal and say, I don't know, capital T equal t over tau. These, well, first off, they become unitless, so you have to be careful about that. But now, all my velocities in the problem will hang as close to 1 as possible. And my times will be like 1, 2, 3, 4, 5. Most likely, I'm probably not going to go past more than, say, 100 characteristic times or something like that. And so my equation of motion would get rewritten as du dt, so we'll call that u prime rather than u dot because this is a scaled time that I'm using, is equal to 1 minus u. And then I would go ahead and solve that. Similarly, for a quadratic case, I would just square that up there. Okay, so again, when you're using something like Mathematica, it's not a big deal, except that Mathematica will anti-oops you. If you overflow or underflow, it has an arbitrary precision package that it uses, but it is incredibly costly in terms of computer resources. It can take you easily 20, hundreds of times longer to calculate something using arbitrary precision than it would for you to instead calculate it, keeping it in machine precision. So even when you're using Mathematica, something to keep in the back of your mind if you start getting out of the realm of machine precision, start looking at doing scaled values. Okay. So let me go ahead and work a few examples of this. So let's go ahead and look at air resistance. And we're just going to imagine dropping a basketball here. So we'll start by, format, looking at one-dimensional motion. Alrighty. So after having said all that, I'm going to promptly ignore my own good advice. And we can go and take a look at it. So I've calculated the so let's go ahead and come up with some parameters. I usually just call that a list called parms. So whenever I have g, we're going to make that equal to negative 9.8. And for good values for basketball, I worked out that C1 should be something on the order of 3.875 times 10 to the negative 5, not 15, 5. And C2 works out to be pretty good as 0.0138. The mass of a basketball is about 0.6 kilograms. Let's say we launch it at 10 meters per second. And then just for later, when I decide to do this in 2D, we'll make the launch angle 45 degrees, but we're not using that bit right now. Okay. All right, so it happily knows all of those. So now I can make my system. We can say that it's m times v prime of t double equals, because remember we're asserting inequality, we're not assigning, mg, and v of t is asserted to be equal to y prime of t. Okay, so that's my system. All right. So now I can go ahead and get myself a solution, for a numeric solution for this if I want. Your absolute favorite thing in the whole universe is nd solve. We'll ask it to solve this system with the parameters substituted. And we will require that initially we're moving at v naught. And we are starting at y equals 0. And I want solutions for y and v. And we'll run it from t is 0 to, say, 100 seconds. That should be more than enough. All right. So it spits out that has these nice interpolating functions, which is just a fancy way of saying, dude, I solved it for a bunch of points. And there's your answers. So you can see it puts a tiny little plot right here just so you've got some idea of it. But let's go ahead and actually just plot them. So we'll plot, let's say, v of t substituting in our solution. And we'll run it from t equals 0 to, I don't know, where's a good point to do it? Let's go ahead and, I'm sorry, well, t of 0 to, to the turning, where it hits the ground again. So we'll find when it hits the ground by finding the root of y of t for our solution is identically 0. So that'll be the time that it hits. And then we need to give the root finder a hint as to where that is. We'll tell it to look somewhere between around, say, I don't know, 1.5 seconds. That may or may not be a good guess. Basically, I just want far away from time 0. Okay, there we go. That looks nice and plausible. And then while we're at it, copy, paste. Let's also make a similar plot for y of t. There we go. That looks pretty. And you'll notice it's kind of what we've expected. You get a bit of a parabola, but you notice that it does indeed hang for, it takes a little longer to come down than to come up, which is what we were expecting. Okay. All right, now we can go ahead and instead, let's go and do it for quadratic air resistance. And I think you'll see that'll be a much bigger deal there. So we'll copy that. Oops, I'm sorry, that was just basic free. My bad. That was just basic free fall, and it behaved exactly the way we expected. Yeah. Now let's go ahead and do quadratic air resistance. All right, so for quadratic air resistance, the system is now going to be mg minus, now here what I'm doing is I have to get the right plus or minus sign, and the sine function returns +1 if the thing's positive, -1 if the thing's negative. So the sine of v of t, we'll times that by c2, and then we'll times that by v of t squared. And everything else stays the same. Alright, so the nice thing about putting everything in nice little parameters like this is that I can go ahead and steal the code. There we go. And just do it again. And there's my answers there. And we can already see from the preview, this is looking really hanky. You can see that it goes kerplop pretty fast. So we'll just go ahead and we'll steal this cell right here. And fortunately, we'll exclude sort of the crappy area because we'll find where it hit. And that looks more reasonable. Now you can see that, yeah, we took longer to come down than we did to come up. Again, not by much because I'm trying to use real world values. Now, here's the bit that we couldn't do. So I should probably label this right here so we know what we're doing. Let's go ahead and do the combined. Sorry, format. Again, subchapter. And then I need an input cell. Okay, good. So again, we can just do the same old thing of just doing loot and plunder. So we'll copy, paste, and now I just need to throw in the new wrinkle. That'll be the C1 V of t. There it is. We'll solve it. Okay, it said it didn't like me too much, but it didn't like me out over at 28 seconds. So that's probably okay because we know that we really only need to look out to about 2 seconds. So I'll just tell it, all right, just do it for 10. And now it doesn't mind me so much. All right, and then we do this. We go ahead and plot the solution over the physically meaningful area. And it doesn't look too much different, which is sort of what we expect. It just tells us that you can see it added a little bit here. We're just past 2 seconds now, whereas before we were at what? Maybe 1.92, so about an extra tenth of a second is what the linear drag did. So, probably its effect probably more came into play in the last few tenths of a second here, and I'm sorry, in the few tenths of a second around the turning point here when the speed was kind of low. Okay. Now we can go ahead and do two-dimensional motion. Yeah, let me put a chapter head in here too, or subchapter, no drag. All right, so now let's go ahead and do two-dimensional motion instead. Pardon me for